Hey there, it's going to be section 1.3 here. We're going to be talking about different properties of radicals, whether they be square roots or other roots, how do we deal with rational exponents, how do we deal with rationalizing denominators. So a whole bunch to deal with like properties and rules regarding radicals. So, and just think about what a square root is, why it is what it is when we say the square root of 36. What we're really looking for is, because 36 is 6 times 6, or 6 squared, and so then square roots and squares are inverses of each other. They cancel each other, so of course that's just 6. So what number times itself is 36? Well, that number being 6. So the same thing here on the first example, the square root of 225. Well, 225 is 15 times 15, and so the square root of 225 must be 15. What about the square root of the square root of 81? So if you think about what that means, that'd be the square root of 9 times 9. Well, the square root of 9 times 9 is 9, and so I still have that outer square root, which I guess would have been like this one. So I still have that one. And then the square root of 9, which of course is the square root of 3 times 3, which is just 3. So the square root of 81 is 3. The square root of 25 minus 9, so simplifying that first. Square root of 25 minus 9 is 16. Of course, square root of 16 is 4 times 4 is 16. So the square root of that would be, 4. And then the square root of 36 plus the square root of 121. So I need to simplify that first. Of course, square root of 36 is 6. Square root of 121 is 11. So then 6 plus 11 would be 17. The product rule for radicals is that it says that the square root of a product, like a times b, can be broken apart into the square root of a times the square root of b, which will allow us to do something like the square root of 200. Well, I know that the square root of 200 is, 200 is 100 times 2, and we know the square root of 100 is 10, so we could reduce or simplify that. So the square root of 200 reduces down to 10 times the square root of 2. Those of you that had me last year, this is where we would have done stuff with the sock method in order to get here. This is just a different method, and it's often faster if you're good at recognizing your square roots. If you're not so hot on that, if you want to go back and use the sock method, you certainly can. And if that's something you need help with, you need to let me know. The quotient rule is pretty similar. If we have a square root of a quotient, we can break that apart into just the square root over a square root. Something that looks pretty complicated, like the square root of 16/9 actually turns out to be really simple. It's just the square root of 16 over the square root of 9, which is just 4 over 3. So, this is just simplifying these expressions. This is all something you guys have done before. What we can do is take that product rule to break these things apart. Sometimes that's the easiest way to think about it. If I think about that's the square root of 50 times the square root of x squared times the square root of y cubed times the square root of z. Well, we take that square root of 50 and say, well, that's the square root of 25 times the square root of 2. And I'm going to go ahead and just keep working with that. Well, I know the square root of 25 is 5, and the square root of 2 is, I can't do anything with that. Well, the square root of x squared, right? Well, that's just the square root of x times x, which we know is x. And since there was multiplication here earlier, I'm going to bring that down. It's going to be multiplication here as well. Square root of y cubed, well, that's the square root of y squared times the square root of y. Well, why did I break the square root of y squared out? Well, because I know what the square root of y squared is. All right, the square root and the square cancel each other, and we're left with just the y here. Just like we could have skipped this step here and said, well, those cancel, I'm left with just an x. So those cancel. I'm left with just a y. So I can bring that first y out. And then I have this second y that's still in a radical here. I didn't even talk about something earlier. Oops. And then the square root of z. Well, there's nothing I can do with the square root of z. So that's just going to drop straight on down. What we can do with all this now is we can use the product property in reverse. They can take all the stuff that's on the outsides, and that can all go on the outside together. So 5x and y are all on the outside. And then I have my radical still. Let's see what's left on the inside. Let's see, I have a 2, and a y, and a z. So 2y, z is on the inside. So the square root of 50x squared y cubed z simplified down to 5xy times radical 2y z. Let me scoot back at the top. I forgot to talk about something. When you're looking at a radical expression, it's made up of 3 parts. So the radical itself is the symbol that we use to denominate square root or a root. Okay, so that's the radical. The index is tell us what root we're taking. So when there's no index, it's implied to be a 2. So there's a little secret 2 right there. If it's anything else besides 2, like 3, 4, 5, 7 needs to be written. Okay. There's no negative indexes. There's no decimal indexes. And there's no such thing as an index of 1 or 0. Okay. And then the radicand is the number or expression inside of the radical. What are we taking the square root or root of? So in this case, the radicand would be 225 or 81. Okay. Square root of 50x times the square root of 2x. So if we kind of break things apart, we know that the square root of 50x can be rewritten as the square root of 25 times the square root of 2 times the square root of x. And then the square root of 2x can be rewritten as the square root of 2 times the square root of x. If we want, there's so many different ways to do this. One way we could do is to take all the number pieces and put those together. So if we think about 25 times 2 times 2 would be 100. So that could be rewritten as the square root of 100. And we can take all of the variable pieces and push them together. So this x times x being x squared. So we times the square root of x squared. And then, well, the square root of 100 is 10. Square root of x squared is x. So it must be equal to 10x. Yeah, so many different ways we could have approached that, but that's just one way. The square root of 2x squared over 9y to the 4th. Again, really it kind of starts off with the breaking apart. So I want to think about the fraction itself is, breaking there. And then on the top of the fraction, I'm going to look at this. I'm going to break that part of the radical apart. So I'm going to say that's the square root of 2 times the square root of x squared. And then on the bottom, I'm going to take that and I'm going to break that apart. So that's the square root of 9 times the square root of 9, or of y to the 4th. Again, just like I'm trying to run through all the different ways I can think about talking about this. There's just so many. If you think about what y to the 4th is, it's probably the most complex part of this right now. Well, y to the 4th could also be rewritten as y squared times y squared. So this could be the square root of y squared times the square root of y squared. So that's just, again, one way we could do this right now. And then going from there to simplifying what we can. The square root of 2 cannot be simplified, but the square root of x squared can be. The square root of 9 can be. The square root of y squared can also be simplified. So the only thing that's not simplifiable here is that square root of 2. So we know that the square root of x squared is x. So that x is going to jump to the front since it's outside of the radical. the square root of 2 is going to stay put. We never write numbers, variables after a radical because we don't want it to look like this. And then you start to question about if that x is supposed to be inside or outside of the radical. It's not good depending on how well somebody did, saying, hey, that's where the radical stops. So we always move things like that into the front of the radical so that there's no confusion. Like it's very clear here that the x is not under the radical. Here you're like, I don't know, could be some bad handwriting. It's hard to know. So don't do that. And then, well, square root of 9 is 3. And the square root of y squared is y. And the square root of y squared is y. So on the bottom we have 2y squareds, or 2y, sorry, which will give me x over square root of 2, or x squared of 2 over 3y squared. And then last one of these, so looks like it's already broken apart into two different top and bottom, so you don't need to worry about that. Again, just what I'm probably going to do is just think about this in pieces. You don't definitely need to like actually sit there and write all this out, but it's just really that idea that you're thinking about this in pieces, which is the big thing. I'm going to think about the A piece and the B piece and the 9 piece like separately from each other. The 3 and then the A and then the B here. We'll just kind of separate those. So square root of 9, of course, don't really need to break that down. I'll just leave that as it is. Square root of a to the 5th. So if I think about a way to break that down that could be helpful, will be the square root of a to the 4th times the square root of a. And why that's helpful is because this has an even exponent. And we know how to deal with even exponents as far as roots. A little bit easier, or square roots. And then square root of b to the 14th, well, that's already even, so I can just leave it. Square root of 3, can't do anything about that. On the bottom, square root of a to the 4th, that's already got an even a exponent, so I don't need to worry about anything there. And b to the 5th, that's not an even exponent, so I'm going to break it down, and so it is, so b to the 4th times b to the, just b. And then things that are reducible here, square root of 9 is, square root of a to the 4th is, square root of b to the 14th is, square root of a to the 4th is, square root of b to the 4th is. Those are the things that are reducible, so I'm going to deal with those first. Square root of 9 is 3. Square root of a to the 4th. So what times itself is a to the 4th? Well, a squared times a squared is a to the 4th. So the square root of a to the 4th is a squared. Square root of a is not reducible, so I'm skipping over that right now. And I'm looking here, what times itself is b to the 14th? Well, that would be b to the 7th times b to the 7th. So I'm going to get 1 b to the 7th out. And then I would have my square root of a. That would be my numerator. On the bottom, what was reducible would be the square root of a to the 4th, and that's a squared, like we talked about already. Square root of b to the 4th, so what times itself is b to the 4th? That'd be b squared. The square root of 3 and the square root of b, neither one of them reducible. We're going to push those back together, and we get the square root of 3b. Okay. And then from here, just like we saw in 1.2, we have some like terms essentially where we have b's on a's on the top and bottom, so those need to reduce. And we know that division means subtraction, so here we'd have 2 minus 2, which really would just cancel all the a's. And then here we'd have 7 minus 2, which would cancel those and leave me with 5 b's on the top. So final answer here, 3b to the 5th square root of a over square root of 3b. This is actually not done, but it's as far as I'm going to go right now, just because we haven't talked about something else that needs to be done with it. But just some things maybe to clarify right now. These 3's cannot cancel because this is a normal 3 and this is a square root of 3. So this is actually not even equal to 3 right now. And these b's, same thing. This, b can't cancel with the square root of b. So those don't get to interact. So if you might have been thinking that. I would like you to try to fill in this part. So look at page 34 and 35 in your textbook and try to find what you need to fill in here, and then do these 2 examples on your own. And then let me know how that goes. Next thing we're going to talk about is how to rationalize the denominator. So what we're looking at here is that when a rational expression contains a single radical term in the denominator, so what I mean by that is like a single radical term, like it's just the square root of 2 versus something a little bit more complex, like 2 plus the square root of 3. We're going to multiply the numerator in the denominator by that radical in the denominator. So in order to get rid of the square root of 2 or make it rational, so right now the square root of 2 is irrational, so we're going to try to find a way to make that rational. We know that the square root of 2 times the square root of 2 is just 2. Okay? Remember, there's a really neat little trick, like square root of 5 times the square root of 5 is just 5. All right? And so we can make something that's irrational rational by multiplying it by itself. So we're going to use that to make this a rational number. So I'm going to take 12 square roots of 3 divided by square root of 2, and I'll multiply it by the square root of 2 over the square root of 2. So the idea here is by doing this, I'll turn this into a 2, and I have to put this here because otherwise this wouldn't be equal to 1. So because I'm multiplying by square root of 2 over square root of 2, I'm really just multiplying by 1. So I'm not changing the value of this, I'm just changing the way it looks. So we want to get that 2 out of square root of 2 out of the bottom and replace it with just a plain old 2. So square root of 2 times square root of 2 is 2. On the top, we get 12. There's just a 1 right here. So 12 times 1 is just going to be 12. And then square root of 3 times the square root of 2 is the square root of 6. And then when we look at this, we need to reduce this fraction. Remember, radical numbers do not interact with normal numbers. The normal numbers can interact. So as I go to reduce this, the 12 and the 2 will reduce, the 6 inside the radical will stay put. So we end up with 12 divided by 2, which is 6, square root of 6 over 1, but we're not going to put the 1 there. So there's our final simplified answer. A little bit more complex with the rational and irrational part here. We're going to use we're going to do something similar. We're going to multiply the denominator and the numerator by, but this time it's the conjugate of the denominator. And what that means when we say conjugate is that something like 4 plus the square root of 7, its conjugate would be 4 minus the square root of 7. This is something we did last year in Algebra 2. We also worked with this when we were doing stuff with I. We talked about conjugates, so this shouldn't be brand new to you. Again, just time has eroded some of this, but really the big thing is you've got to change the sign. If you don't change the sign, you're not going to get it right. And it's just the one sign. It's only the sign in the middle that changes. If that had said 3 minus the square root of 2, its conjugate would be 3 plus the square root of 2. Okay, so you've got to change that sign in the middle. So that's what I'm going to do here. So I want to get this to be, I want the denominator to be rational. Right now it's irrational. So I'm going to take 7 over 2 plus radical 3, and I'm going to multiply it by 1 so that I'm not changing its value. So multiply that by the conjugate, which is 2 minus radical 3, and 2 minus radical 3. So this is all equal to 1, so I'm not changing the value of this, but I'm going to find a way to rewrite this to make it rational. So on the top, that's kind of the easy part here with this particular problem. Let's see, that will be equal to, on top, essentially we just need to distribute. 7 times 2 is 14. 7 times negative radical 3 would be negative 7 radical 3. The 7 does not go inside the radical since it's not a radical number itself. It just kind of interacts with the 1 that's in front of there. On the bottom, let's see. Essentially just need to FOIL here. 2 times 2 is 4. 2 times negative radical 3 would be negative 2 radical 3. Positive radical 3 times positive 2 would be positive 2 radical 3. And then positive radical 3 times negative radical 3 would be negative. So radical 3 times radical 3 is 3. And we start to see why this works here because of this. These two terms will cancel each other out, and leaving us with just integers. So those are gone. And on the top now, we see 14 minus 7 radical 3, and then over 4 minus 3, which of course is just 1. So I could just say that's this. Just a little word to the y's, like if we had ended up with like 14 minus 7 radical 3 over 2 or 4 or something like that. Just happened to end up with 1 there. It's just right, nothing special about that. So if we'd ended up here, we can't do any more because the 14 and the 7 are both not divisible by 2. There's nothing to do here. So you can't just divide this part. That's not okay. You'd have to be able to divide everything here. Okay. So if it looked like this, let's say we had like 14 minus 8 radical 3 over 4, something like that. So because the 14, the 8, and the 4 all have 2 in them, notice how I'm just looking at the normal numbers. I'm ignoring the radical number. These all have 2 in them. I can reduce that by 2. So that would be equal to 7 plus, not plus, minus 4 radical 3 over 2. So not reducible because these don't all share anything. Reducible because these all do share anything. You know, and here this just became a 1. So I just ignored it since everything is divisible by 1. So that's rationalizing a more complex denominator. Simplifying other roots. Again, we would have done this already, in Algebra 2. Again, we usually would have talked about the sock method. What I'm talking to you guys today is more about the that product property method, which requires you to know some roots, and I'll talk to you guys about that in class, how to know some roots. But if you know, like what's 1 times 1 times 1, what's 2 times 2 times 2, what's 3 times 3 times 3, what's 4 times 4 times 4, what's 5 times 5 times 5, or what's 6 times 6 times 6. So 6 times 6 times 6 is 216. Well, negative 6 times negative 6 times negative 6 is negative 216. So the cube root of negative 216 is negative 6. Cube root, or the fourth root of 3 times the fourth root of 80 divided by the fourth root of 5. Okay, so how many fourth roots do you know? Probably not that many. But 1 times 1 times 1 times 1 is 1. 2 times 2 is 4. Times 2 is 8. Times 2 is 16. And 16 times 5 is 80. I'm going to rewrite this as 3 times the 4th root of 16 times the 4th root of 5 all over the 4th root of 5. So what happened there is I recognized that 16 times 5 is 80, and 16 is a perfect 4th root, or a perfect 4th power, because 2 to the 4th is 16. Okay. What that also helps is that because I have a 4th root of 5 divided by a 4th root of 5, those just cancel. This is equal to 2. So where that ends up is 3 times 2, which of course is 6. And I'm going to talk to you a little bit about recognizing this, how you're going to do that, maybe a little faster. Or again, if you're really worried about being able to do that, you could always use the sock method. So here I have some cube roots. So I want to look for a perfect cube that goes into 9,000. And 10 times 10 times 10 is 1,000. So this is 6 times the cube root of 1,000 times 9, cube root of 9, plus 7 times, I need a perfect cube that goes into 576, and we all know our factors of 576. It turns out the perfect cube that goes into 576 is 64. 64 times 9 is 576. And so, and 64 is 4 times 4 times 4. So it's a perfect cube. And so what I see here is that I got a 6, of course. The cube root of 1,000 is 10. And then there's no cube root of 9, so that's still just the cube root of 9. And then plus 7. The cube root of 64 is 4, so times 4. And then that cube root of 9 again. So I have 60 cube roots of 9 plus 28 cube roots of 9, because the index and the radicand are the same. I can add these things. Right? If I just think about this as an apple, I have 60 apples plus 28. That same apple, that would just give me 88 of those apples. Well, it turns out my apple is a cube root of 9. Right? So out of 88 of those, it's almost like it says 60x plus 28x. Right? 60 times something plus 28 times that same thing is the same as 88 of those things. So the thing didn't change, just how many of them I had did, just combining like terms. The term does not change. So there's some operations with different roots. And the last thing is rational exponents. It's something we've talked about before. How do we move between rational exponents? So rational exponent is a fractional exponent, and I do want you guys to be careful about how you write that. I'm not the biggest fan how they're really hard to type. So when you're writing that, make sure you don't write 9 and like 5 halves like that. That's a mixed number. You need to make sure you write it like 9 and then like that, so it looks really clear that that's a exponent. Okay, so be careful about that, please. So how do we deal with like 9 to the 5 halves power? Like, what the heck does that mean? So when you talk about fractional exponents, the denominator of the fraction is the index of the root, and then the numerator of the exponent is just the exponent. And so this would be the nth root of a to the mth power, or I really prefer it this way, where the nth root of a all to the mth power. So a different way of looking at it with numbers instead, usually a little easier. 27 to the 2/3 power. So the 3, the denominator is the index. So that's going to go here on the radical. So I rewrite that as the cube root of 27, and then all to the 2nd power. So I kick that 2 to the outside. Now why I do that is because it forces me to do the inside first. The cube root of 27 is 3, and then the square is still there, and then 3 squared is 9. So this is how we're going to evaluate these expressions with rational exponents. Going to turn them into radicals. So write 9 to the 5 halves power as a radical, and then simplify it. So 9 to the 5 halves, so that's going to be, I'm going to write root and then a 9, and then remember the 2 there goes on the index. Normally we wouldn't write a 2 there, but I'm going to do that. And then the 5 goes on the exponent. So there's one way we could write it. Again, I'm not a big fan of that way. I prefer that you write it this way, where we take that 9 with the 2 on the index, and then you throw the 5 on the outside. So remember, this is a square root. It's the normal root. We don't normally put the 2 there. Okay, so even though we did, it doesn't change the math. It's still the square root of 9, which of course is 3. And so we have 3 to the 5th power, which is 243, using a calculator or whatever. If we'd done it this way, we'd have to take 9 to the 5th power, which is some giant number, and then try to find the square root of that giant number. Not super easy. Okay, so that's why I prefer this way of writing it instead. So here it is as a radical, here it is simplified. So these are the two things I need to see, and this is kind of just the work in between. This is going to be going the other way. So we got x times the square root of 5y all to the 9th power. So what I'm going to do, the x is just going to be kind of hanging out right now. What I need to work on is this, rewriting this with a rational exponent. Remember, there's a little 2 right here. That's my denominator. And this is, the 9 is my numerator. So I have 5y all to the 9 halves power. Okay, so the 9 became the numerator. The index, which was the 2, became the denominator. And then the x is right there. So I'm just going to bring that x down. Probably could simplify it a little more, like kind of spreading things out. So we usually want a number in the front of an expression, not the middle of it. So it'd probably 5 to the 9 halves power, and then x, and then y to the 9 halves power. Yeah, because we do things in alphabetical order, so that's probably the way to write that with rational exponents. And the last one here, you want to simplify this. 8x to the 1/3 times 14x to the 6/5. So what I'm going to do with this, I want to think about pieces. So I got some numbers that are multiplying each other. And I have some variables that can multiply, and they're both x's. That means the exponents will be combined. So start off with just 8 times 14 times x to the 1/3 times x to the 6/5. Well, of course, 8 times 14 is just 112. What we learned about exponents is that when you multiply powers, the exponents need to add. So we need to add 1/3 and 6/5. So we need to come off to the side and say, hey, what's 1/3 plus 6/5? Well, we can only add fractions when the denominators are the same. And so to get like denominators, they'd have to both be 15. So multiplying this by 5, I would then need to multiply the numerator by 5, so that'd be 5/15. And then multiplying the 5 here by 3, I'd have to multiply the numerator by 3, so I'd end up with 18/15. 5/15 plus 18/15 is 23/15. So that would be 112 times x to the 23/15 power. You never, ever, ever write powers as decimals, and you never write them as mixed numbers. So you always leave it as an improper fraction if it's going to be that way. Because remember what this means, this has meaning. This is the 15th root of x to the 23rd power. If you try to turn that into a mixed number, it loses that meaning. Okay, so you got to be careful about that. So here's our final answer. So some fraction addition there. Right. So hopefully that wasn't too bad. It was, seemed like some of that stuff was going kind of fast, and I know I was doing some different methods, and maybe I taught you last year if I had you as an Algebra 2 student. So just different ways of looking at things. Again, there's always your option to let me know if things need to be a different way for you, or if you want to come chat with me. So please do.